Now let's jump into the discussion of a very simple but often overlooked aspect of biological learning. This is not really even a biological concept, it is more of a mathematics concept that has been brought over to biology where we can apply this to biological organisms, and that would be the surface area to volume ratio. It's a pretty straightforward concept, nothing hard. So let me start off by using a small introduction to surface area and volume and what they are. Simply speaking, surface area can just be told as being the total area of an organism exposed to the environment. If you just look at yourself, you're exposed to the environment through your skin. So your total skin surface area would be your total surface area exposed to the environment. On the other end of that spectrum, we have the volume of a singular organism, simply your volume, total internal volume of an organism. That's it. Throughout my days of teaching surface area to volume, the best way I have found to properly make this stick into your mind is using this nice little example. Now on screen on canvas you will see 3 blocks with a nice tabulated schematic. I'll tell you what we'll be talking about specifically. First of all, we will find the surface area of each of these blocks. Then we'll find the volume, and then finally we'll be able to denote the surface area to volume ratio of the mentioned blocks. Right. Now I'll show you what I mean. Here we're talking about the surface area to volume ratio. And so if I simplify this and write it, this is what we're doing. Surface area to volume ratio. Let me go to the right side actually. Surface area to volume. Otherwise, if I erase these, everything's going to be gone. Right. This. In mathematics, we know to denote a ratio, this simply means this, right? Surface area divided by volume. Okay, just wanted to give you that little bit of detail. Surface area to volume means surface area to volume. Surface area divided by volume. Okay, right. Let's focus on this table. Right. Here you can see we have 3 cubes, basically 3 whole cubes. Each of these small cubes are 1 centimeter in length from either side. So let's first of all focus on the first column of this table and let's fill in the surface area, the volume, and then the surface area to volume ratio so that you can get an idea of what we're talking about. Right. How do you find the surface area of a cube? Simply, you find the area of one face. So basically this face, and then you multiply it by the number of sides, right? When it comes to a cube, we have 6 sides. So that into 6. So that would look something like this. Surface area for this cube would be 1 centimeter times 1 centimeter into 6 for a total surface area of 6 centimeters squared. Alright. How do you do the volume of anything? Length into breadth into height. Or length into width into height, same thing. Here, we know each side is 1 centimeter, so 1 times 1 times 1, that is going to be 1 cubic centimeter, cm3, okay, since we're talking about volume, 1 cm3. Now, what about the surface area to volume ratio? Surface area is 6. When you divide it by the volume, 6 over 1 is simply going to yield you a value of 6. Alright. Pretty simple process. It's a mathematical process. Now let's do the exact same thing to the second cube. Now we know that If each of these blocks are 1 centimeters, this cube is going to have a total size of 2 centimeters on either side. Draw a straight line. Okay, that's still not straight, but it's fine. 2 centimeters. 2 centimeters. Same deal. You get the size of one face, the area of one face. Now that face looks like this and it's larger. 2 times 2 and multiply the number of sides. 2 times 2 is 4. When you multiply 4 by 6, that's going to give you 24 centimeters squared. When applying the same method to find the volume, you do 2 times 2 times 2, 2 times 2, 4, 4 times 2, 8. So now the volume is 8 cm 3. Alright, and then when moving on to the final cube, now we have 3 stacked on each side. So total of 3 centimeters on either side. That would be 3 times 3 to find this face. And then you multiply by the total number of faces. 6 sides for a cube, a standard cube. That should give you a value of 54 centimeters squared for the area. With the same approach, if we are going for the volume, 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. Right. Let's calculate the surface area to volume ratios. 24 over 8, which is going to be 3. And then 54 over 27, which is going to be 2. Now, do you notice something? When going from the smallest cube all the way to the largest, our surface area to volume ratio is dropping. Why? The reason being, now do you see, when it comes to surface area, 6, 24, 54 is a kind of an okay increase. It's linearly increasing. But if you look at volume, do you see 1 to 8, 8 all the way to 27, it's rapidly increasing. There's a rapid increase in volume. There's a rapid increase in volume. How would we summarize this? Now, as surface area and volume of an organism increases, the surface area to volume ratio clearly decreases. What is the reason for this? Now, if both of those variables are increasing, shouldn't the surface area to volume ratio also increase? No. Why? That's because since, you see, volume increases much more rapidly. Why does it increase much more rapidly? Because volume is a cubic measure than surface area. Surface area is just a square measure. This is the reason why surface area to volume is such a big deal in biology. When you're a baby, you have a very low surface area to volume ratio. A very low surface area to volume, therefore a high ratio. But the more you become an adult, things reverse. That's the concept of a biological and mathematical approach to surface area and volume.